We have another buoyancy problem here, and the problem states that you are preparing some apparatus for a visit to a newly discovered planet Cassie, and it has an ocean of glycerine, and the density of glycerine is given beside it. And it also has a surface acceleration due to gravity of 4.15 meters per second squared. So this is considerably smaller compared to the acceleration due to gravity. If your apparatus floats in the oceans on Earth with 25% of its volume submerged, what percentage then will be submerged in the glycerine ocean of Cassie? So the answer that we will show is 20.4%. But before we proceed with answering this problem, I want you to recall from our discussion that if you have a beaker such as this one, and that beaker has an initial volume of V1, and then when you submerge some spherical iron ball there, the volume will increase to V2. So you notice the shaded region is your change in volume, which we call as delta V. But that change in volume corresponds to the volume of the spherical object that is submerged. Spherical object that is submerged. Another way of thinking of this delta V, or the change in volume, is this corresponds to the volume of the fluid displaced by the object. So this is the volume of the fluid displaced by the submerged object in that case. Now, let's focus on the problem. Now, the problem do or tell us to compare what will happen on Earth, and the other case is on the new planet Cassie. Now, let's try to gather some information. For Earth, we know that the acceleration due to gravity is 9.8 meters per second squared. And for, I will put it E. For G sub C, meaning on the planet Cassie, it has an acceleration due to gravity which is smaller, which is just 4.15 meters per second squared. Now, another thing that we should remember is that on Earth, when it's allowed to float on the Earth's ocean, on Earth, the volume of the displaced fluid, which I represented as VDF, is equal to zero point 0.5 of V sub O, or the volume of the original object. Now, the question in the problem is how much is the volume of the displaced fluid will be on the planet Cassie. Because why we say that it's basically asking for the volume of the displaced fluid, because you know that how much is submerged in a given fluid, how much of the volume of the object is submerged in a given fluid, in this case, this entire volume also corresponds to the volume of the fluid displaced on that object, on that fluid. To show what I am talking about, consider this case. On Earth, you have, for example, the problem says that on Earth's ocean, if this is the volume, let's just say that it's some, although it's not stated, but let's assume that it will have this regular shape. So this is the portion that is submerged on the Earth's ocean, and that corresponds to 25% or 0.25 of the VO, meaning the volume of the object. But if you try to relate these two illustrations, whatever the volume submerged on the fluid, we know that that is also the volume of the fluid that is displaced by that object on the fluid. Okay, so I'm hoping this is clear to you right now. Therefore, what we are actually trying to solve in this problem is on the glycerine ocean of Cassie, how much is the volume displaced, meaning how much is this one? How much is the volume displaced? Or another way of thinking about that is how much is the volume of the object to be submerged or will be submerged in the glycerine ocean of Cassie. So I'm hoping this is clear to you. But to approach this problem, take note that we have two cases. One is on Earth and the other is on Cassie. Now you should be thinking na what is constant in both of the planets? So we know that what is constant in both of the planets is their masses. That means that the mass of the object on Earth, I'll put it on Earth, is simply equal to the mass of that object, the same object on uh, the planet Cassie. So that is the first thing that you should establish. Now let's try to solve this problem. Take note that on Earth, the object is actually able to float on the Earth's ocean. Since it's able to float on the Earth's ocean, that means to say that at least the weight of the object, W sub O, is equal to the buoyant force because this is the minimum requirement for an object to float. Otherwise, if the weight of the object is very great compared to the buoyant force, then that is the case where it will not float. But since this is a case or a problem in which it floats, at least the minimum requirement that the weight of the object is equal to the buoyant force. But we know that the weight of the object is just mass of the object times the acceleration due to gravity on Earth. And from our previous discussion, we also know that the buoyant force is just the density of the fluid, which in this case is the seawater on Earth, the acceleration due to gravity, which is still, this is the case on Earth, and multiplied by the volume of the displaced fluid. Okay, so we know that this is the equation for the buoyant force, or more commonly, you have it as rho Vg or rho Gv. So it really doesn't matter in this case. So since we have established that the mass of the object is the same whether you are in Earth and you are on Cassie, so let's try to find an expression for m sub o, meaning the mass of the object, which is constant. But we could simplify this one since g is common to both sides, that will just cancel out. Therefore, the mass of the object on Earth is given by the density of the fluid on Earth, which is seawater, multiplied by the volume of the displaced fluid. Now take note that on Earth, it's very clear that the displaced fluid is this small volume here, this one, this part, and that is 0.25 of the original volume, V sub O, of the object. Let's check. Yeah, it's 25%. So what happens for your mass of the object now, M sub O, that will be the density of the fluid on Earth. I will put E here, density of the fluid on Earth, so that we won't be uh, confusing this on the different planet. And then the the volume of the displaced fluid, which is 0.25 of the original volume. So this is the first equation that we arrive from the problem. This is on the case on Earth. Now, let's try to do what happens on the planet Cassie. On the planet Cassie, it still was able to float. That means your object is still able to float. Therefore, as I've said earlier, the minimum requirement that the weight of the object on planet Cassie should be equal to the buoyant force on that planet since it was able to float. This is the minimum requirement. So when we try to expound this equation, we will have mass of the object, which is practically the same regardless of where planet you are considering, but the g will change now. The g will be the acceleration due to gravity on the planet Cassie. And still, the buoyant force, the same equation. You have the density, but this time around, the fluid will be on the seawater of the planet Cassie, which is glycerine. The density of the fluid on that planet multiplied by the acceleration due to gravity on the planet Cassie, and then the volume of the displaced fluid, which is what we are trying to find. So I will put a highlight on that because that is what we are trying to find. So the volume of the displaced fluid corresponds to this part, and this means to say also that the volume of the displaced fluid is the same actually as the volume of the submerged part of the object. So when we look at the equation, we also see the same trend with this one. The GC is common, thus it will be cancelled out. So we are left with an equation for MO, meaning the mass of the object, that is just the density of the fluid on planet Cassie, multiplied by the volume of the displaced fluid, which is what we are trying to find. So we now have two sets of equation. Let me highlight the two sets of equation here. So I'll highlight it in blue. This is the first equation that you arrive on Earth, and this is the second equation that you arrive on planet Cassie. So since the two equations are equations for m sub o, meaning the mass of the object, and we know that the mass of the object is the same for both planets, we could equate these two equations. So that means we could equate the density of the fluid on Earth multiplied by 0.25 of its V naught, original volume, because 25% is submerged in the Earth's ocean. We could equate it with the equation of mass of the object on the other planet, Cassie, which is the density of the fluid on planet Cassie multiplied by the volume displaced of the fluid, which is what we are asking in the problem. Now, when we try to, since this VDF, V sub DF is what we are trying to find, I want to isolate that in either side of the equation, and I can easily do that by multiplying both sides by 1 all over the density of the fluid on the planet Cassie. So when I do that, this density will cancel out, and hence I was successful in my quest of isolating VDF, meaning the volume of the fluid displaced. Therefore, the volume of the fluid displaced is given by the density of the fluid on Earth, and then you multiply it by 0.25 of V naught, where V naught represents original volume, divided by the density of the fluid on the planet Cassie. So what we are going to do next is simply a matter of substitution. Now, the density of the fluid on Earth, which is seawater, is 1.03 times 10 to the 3 kilograms per cubic meters. And then you multiply that with 0.25 of the original volume V naught. And you divide everything by the density of the fluid on planet Cassie. So the oceans on the planet Cassie is having a density equal to glycerine, which is 1.26 times 10 to the 3. So we are going to substitute that here. We have 1.26 times 10 to the 3. Then we have kilograms per cubic meters. So let's try to look into the units. The units for density will simply cancel out, and hence we have a dimensionless number, which is what we expect or what we want, since we are basically comparing the ratio of these two volumes. Okay, so you work with your calculator, so 1.03 times 10 to the 3, and then you multiply it by 0.25, and then you divide it by 1.26 times 1.26 times 10 to the 3, and you will get 0.2044. And do not forget V naught. That means that the volume of the fluid displaced is 0.2044 of the original volume V naught. Another way of interpreting that result is that the volume of the displaced fluid in the planet Cassie is 20.44% of V naught, meaning the volume of the original object. So that means to say that in our illustration, if the orange part that you see here is V naught, the submerged part of that is only 20.44% of the entire volume. That means to say it's 20.44% of V naught. Let's try to check whether we get the same result. And yes, we get the same result. 20.4% of the volume will be submerged on the planet Cassie.